So, hi everyone. I am Anuj Kumar. I am here to discuss today the assignment 3 of this course. Okay. Can you hear me? Anyone of you can please confirm. Okay, that's fine. So, can you see my slides? Okay. So this is the assignment 3 of the coordination chemistry course, right? So today, some some candidates are still joining. Okay, so I'll discuss this assignment for week 3 that is basically related to coordination number and stereochemistry of coordination compounds. Okay, so the pattern will be similar. Okay, so I'll show you the two problems. I'll wait for 2 minutes to get your answers, and after that, I'll discuss as you are already familiar with. Okay, so these are two questions. In first one, you have to determine the basically geometry. So which geometry among these does not belong to the coordination number of 6? You are given the four options. One is octahedral, trigonal prism, square planar, and hexagonal planar, right? And the second one is you have to tell the incorrect statement for the ionic potential. Okay, so from the definition of ionic potential, you can just choose the right answer. Okay. So try at your own to get the right answers. And after that, I'll explain. Just type your answers in the chat box. Okay, I'm not getting any answer. So I will. Okay. First is D. Okay. And what about the second one? Hexagonal planar, as its name indicate, it is metal is coordinated with six atoms of ligand. So that is basically the coordination number 6. Here it is asked which geometry does not belong to. Are you getting my point? Anybody else? Okay. So right. So if you see this is the typical octahedral structure. Okay. So metal is coordinated with the six ligands or six atoms of the ligand. Here, one, 2, 3, 4, 5, and 6, right? And another is, this is typically a trigonal prismatic structure. Okay, this one. Okay, here you can see this is the metal, and these six atoms are of the ligands. So here is also the coordination number is 6. In case of octahedral, it is also 6, and in hexagonal planar, right? This is a metal, this one. Okay, so these all ligands will be in a uh, will be coordinated in a planar fashion. Okay, so what about the square planar complex? Okay, in case of a square planar complex, the coordination number is 4, right? So this geometry does not belong to the coordination number 6. Clear? And the second one, if you see the definition, ionic potential is just the ratio of electric charge to the radius of an ion. Okay, so basically, ionic potential is depending on both the electric charge and the ionic radius also. Okay, so the options are, it is a ratio of electric charge to the radius of an ion. This is correct statement. Increasing the charge, the bond will be stronger. It depends on the charge of the ion. This is also stronger. It does not depend on the size of ion. Basically, it depends on the radius, right? And increasing the charge, the bond will be stronger. Okay, so basically, this ratio measures the charge density at the surface of the ion. Okay, so usually the denser the charge, the stronger the bond formed by the ion with ions of opposite charge. So it depends on both the electrical charge and the size of the ion. Okay, right? So what is the incorrect statement? This one. Clear? So the last one is the incorrect statement because the ionic potential depends upon the size, right? So I am moving forward to the next two. The first one is, what will be the geometry of boron trifluoride molecule and the product when fluoride anion is added to that. Basically, it forms BF3 plus, it is just forming this one. Okay, so BF3 is particularly a Lewis acid. Okay, and it is electron deficient, so it can make the bond with fluoride ion. Okay, so you have to determine the geometry of this one. Sorry, you have to determine the geometry of this one and this one, right? So the options are, first is trigonal, planar, and tetrahedral. Both are planar, both are tetrahedral, and the last one is tetrahedral and the octahedral structure. In second one, what will be the coordination number of the produced complex when two phenylphosphine molecules, triphenylphosphine molecules, are added with this palladium chloride, right? So you have to tell me the coordination number of the complex which is produced after reacting this one with the two molecule of triphenylphosphine. Okay, trigonal, planar, and tetrahedral, right? and 2 is B. Okay. So anybody else is there who wants to give the answer? So look, so BF3 molecule is formed by the bonding between three sp2 orbitals of boron and p orbital of three fluorine atoms, right? So as a result, the hybridization will be sp2. And what is the geometry of sp2? That is trigonal planar. But when this fluoride ion is added, then BF4 negative is formed and geometry will be tetrahedral because the four to accommodate these four atoms of fluorine, the molecule will be forming the tetrahedral structure. Okay, so the right answer will be first one is trigonal planar and second one is tetrahedral. Okay, if I discuss about the second one, okay, so when two triphenylphosphine molecules are added with palladium chloride, then this cis complex is formed. Okay, here there are two chlorine atoms, chloride ions, right? And one phenyl ring is there, second is this one, and third is this one. And this is a phosphorus molecule, phosphorus atom, right? And similarly at the left side, okay? So the complex, the cis complex is formed, okay? So here, four ligands, two chloride and two triphenylphosphines are attached to the central palladium metal ion. And what about the coordination number? Because it is attached to four atoms of the ligand, so the coordination number will be four, right? So this the B option will be the right answer for this. Okay. So the next question is related to the Vasquez complex. Okay, you have to basically tell the nomenclature of Vasquez complex. Okay, the first one, and the second one, the normal questions you have to identify the ambidentate ligand. Okay, so just try to get the answer and tell me. Vasquez complex is iridium based complex, right? The structure of this Vasquez complex should be in your mind, and just write it, and you can easily get the nomenclature. So, this is the explanation. Vasquez complex is the trivial name for the chemical compound named trans chlorocarbonyl. And why it is trans? Because you can see this is a chloride molecule, a chloride atom. It is a carbonyl ligand. So they are trans with each other. Okay, and the formula is IRCl P triphenylphosphine twice, right? So there are two molecules of PPS3, right? This is iridium, this is chloride, and this is CO, and here it is one phosphorus, it is another phosphorus, right? So what will be its name? Its name will be trans chlorocarbonyl because there are two bulky ligands here. So bis triphenylphosphine iridium and oxidation number is 1, right? So basically it is a square planar complex. Okay, so what will be the right answer? This one, transchlorocarbonyl bis triphenylphosphine iridium 1. Okay. And what about the other one? So ambidentate ligand, the ligand which has two different donor atoms, and either of the two donor atoms, only one atom is attached to the metal during complex formation. Okay, in you can see if there is a nitro ligand or nitrito. Okay, so in this particular one, the nitrogen can only bind to the metal. Okay, and in the second one only oxygen can bind to the metal. So these type of ligands are called as ambidentate ligands. Okay, so first you have to identify which ligand has two different donor atoms, right? So in chloride it is only a single atom. Oxalate, this one, only oxygen is there. Ethylene diamine, only nitrogen is there, right? So in nitrito you have two options. Metal can coordinate with nitrogen, either nitrogen or oxygen. So this will be the ambidentate ligand, right? So now moving forward to the next, the coordination number and the geometry of this complex, vanadium complex. Okay, you have, I think this structure has been discussed in the class. Okay, so just tell me the answer and try the second one also. Which molecule can show Berry pseudo rotation? Basically, Berry pseudo rotation is observed in the trigonal bipyramidal structures. The molecule who show this type of geometry, they can show the Berry pseudo rotation. And what is Berry pseudo rotation? Basically, the axial bond changes to the equatorial, and equatorial changes to the axial, right? So their interconversion is there. This phenomena is called Berry pseudo rotation. So basically, you have to identify which compound will show the trigonal bipyramidal structure. Although square planar also show the this one, but in that particular case, you have to identify the trigonal bipyramidal structure, and you will get the answer. If you know the answer, just type in the chat box. To its C. Okay, that's right. And what about the first one? First is A. Okay, I will discuss. Okay, so this is the typical structure of this complex. Okay, this consists of the just this vanadilyl group VO plus two, this one, and four oxygen are attached to the this metal center, which are coming from the this ligand acetyl acetone, right? So the total five oxygens are connected to the central vanadium ion. As a result, the coordination number is 5 and the geometry is square pyramidal. Okay. And this complex, the structure of this complex has been discussed in the class. Okay. So you have to just remember. And what about this one? Because this molecule show the trigonal biopyramidal structure, so that it will show the Barry pseudo rotation. Okay, so as I have already explained, this rotation is a classical mechanism for interchanging axial and equatorial ligands in the molecules. Okay, it most commonly occurs in trigonal bipyramidal geometries, although it can also occur in the molecules with a square pyramidal geometry. Here, only this phosphorus pentafluoride has the trigonal bipyramidal geometry and shows the Barry pseudo rotation. Okay, so you can see this is the typical structure. This is a rotation one. This fluorine atom, and this fluorine atom has been rotated this side. And after this rotation second, you can see this red one. Okay, and these are the equatorial bonds, right? And these are the axial bond. Okay, so the axial has gone to the equatorial side, and equatorial has gone to the axial side. So this is phenomena is called Barry pseudo rotation. So it is typically showed by the trigonal bipyramidal structures. Okay. So moving forward to the next one, you have to identify the correct statement for tetragonal distortion, which you will study in detail when you will study the John Taylor effect. Okay. And these are the four options. It happens for the presence of an extra electron in this orbital. Okay. So basically, you know, there are five orbitals in D, right? One is dxy, dyz, dzx, dx square minus y square, and dz square. Okay, and this distortion occur for the John Taylor effect. It is observed in the octahedral complexes and all of these. Okay, and the second one, you have to identify the geometry. Okay, which among the followings which show the trigonal prismatic complex. Just try to get the answer by yourself. I'll wait for 2 minutes, right? Anybody who can give the answer for these two questions? You can just try the second one also, because the structure of this one has been already discussed. Okay, in class. So basically, what is a tetragonal distortion? If you are having this one is a octahedral, regular octahedral geometry, and if these bonds are elongated along z axis. Okay, so this will be your tetragonal distortion, or you can say elongation. Okay, distortion can be elongation or compression. This bond can have a distance less than the distance in the case of regular octahedral. Okay, so basically this phenomena occurs due to the John Taylor effect, and which arises due to the unsymmetrical distribution of electrons in the orbital of center metal atom. Okay, same thing. uh, Here the case is shown. You can see these two bonds have a larger distance as compared to the other four bonds, right? So this is a typically a case of tetragonal elongation. Okay, so the distortion in the case of octahedral complexes is also called tetragonal distortion. This happens because of the John Taylor effect when an extra electron is present in the this orbital. Okay, so if you are having any extra electron in the orbital dz square, basically this is this shape is along the axis. The shape of this dz square orbital, it is along the axis. If you are having a electron density, that means extra electron, so what it will do, it will repel the incoming ligands. Okay, so due to that repulsion, this ligand will be moving this side. Okay, and you can say this bond will be elongated, right? And in another scenario, if I talk about the electron density is less, and the electron density on this axis is more, okay, so this bond will be compressed. So that is basically a distortion phenomena. Okay, so more detail you will get when you read the John Taylor distortion. In which particular case you will get the John Taylor distortion, and hence the distortion in geometry. Okay, the second one is, okay, so the you have to identify the trigonal prismatic complex. So typically, I have discussed the this is the trigonal prismatic structure. Okay, and here you can see there are six methyl molecule that is directly attached to the tungsten, which is central metal atom. Okay, so here the six atoms or ligands are arranged around a central atom, defining the vertices of a triangular prism. Okay, so here this is the first example of a molecular trigonal prismatic complex where the six carbon atoms are arranged at the vertices. Okay, so you have to remember the geometry. Basically the geometry changes due to for minimizing the inter-electronic repulsion between the ligands, right? So this type of geometry you are getting accordingly only for minimizing the repulsion, right? If you are having very bulky molecules, okay, so what they want, they basically repel each other, and the optimization in geometry will take place, and you will get a newer geometry, right? Here in the case of methyl also, you just the regular octahedral is not observed, although this molecule is stable in the trigonal prismatic molecular geometry, right? So the next one, how many different geometries have been observed in metal complexes of coordination number 3? Okay, so what are the possible number of geometries you can observe for the 3 coordination number? And second one, you have to uh, just draw the structure of Wilkinson catalyst and get its geometry. Okay, If you know the answer, please tell me. Okay. Yeah. Only one candidate is two, three are giving the answer. Four. Just try to get the answers. Okay, so what are the possibilities of coordination number three? Right? If I am having a coordination number of three, so you can have a trigonal planar structure. Okay, you can have, so you can have this type of structure, right? These are the ligands. Okay, and you can have a T-shaped structure also, right? So basically, three geometries are possible. Okay, just try the second one. What is Wilkinson catalyst? And just read its application. Okay, it is basically used in the cis hydrogenation of alkenes. Okay, so but the question is asking about the structure and its geometry. Okay, so you can see this is the typical structure of Wilkinson catalyst, right? So here, this is the rhodium metal atom, this is chloride, and three triphenylphosphine molecule are attached. Okay, and you can see this geometry is square planar. Okay, so this is Wilkinson catalyst, right? And the coordination number is 4. Geometry is square planar. Okay, and what is the metal? Rhodium. Okay, just so identify. And RH PPS3 whole thrice chloride and square planar. And the answer for first one is 3. Okay, just moving forward to the next two. So these two questions are related to the point group. Okay, so point group, what is point group? Point group basically tells us about the geometry. Okay, let's say if you are having a C3V. Okay, C3 means the formula is 360 divided by n. If you are having a C3 symmetry, okay, so 120 degree, right? What does that mean? It means if you rotate any molecule by 120 degree, you will be getting the same structure. Okay, so I can say the particular structure is symmetric with respect to the C3 axis, right? And if I talk about this one, that is V. Basically it denotes the vertical axis. Okay, this is a mirror plane. Okay, something like this. If there is any plane, vertical plane, okay, uh, and if you just see the mirror, okay, if some entity is here and another, and if you see the mirror images, okay, is here, okay, and if there is this type of symmetry, you will get the vertical axis, and collectively this will tell us about the structural information. Okay, if you want to read more details, just read group theory. Okay, here you have to just remember the geometry of a square anti-prismatic structure, and in the second one you have to tell the symmetry in this particular molecule, basically the this metal atom that is attached to the 9 hydrogen atoms, right? Okay, so if you know the answers, I will be very happy to know. Otherwise, I'll discuss. Anybody? Okay, right. I got the answers for the last slides. But try for this one. Or if you are saying that you have sent the answers for this particular slide, you can just ignore. Okay, so I'm waiting for the answers of others. So, right. So here you can see this is this typical structure of square anti-prismatic, right? So here we have taken the example of this zirconium atom connected with this 8 fluorides, right? You can see here there is a principal axis that is C4. So what does that mean? If you rotate this particular molecule 90 degree, you will be getting the same geometry or same structure, right? And if you are getting this, these are four C2 axis. Okay, basically D4D is C4 plus 4C2 plus 4 mirror plane, and one is sigma D. Okay, so the dihedral angle. Okay, so you can see there are four C2 symmetry in between these two metals, sorry, two atoms of fluoride. Okay, and this particular complex is also having the structure of square antiprism and showing D4D. Okay, so and square antiprism has typically a symmetry of D4D, right? And similarly, if you see the structure of uh, this complex, that is showing the coordination number of 9, okay, that is basically showing the D3H geometry. Okay, it will be very easy for you if you just prepare the models of these geometries, and easily you will be getting the symmetry. Okay, so I have taken the typical example for this particular point group, that is D3H. Okay, so PCl 3 molecule, right? So you can see one C3 axis is there, symmetry, and C3 plus 3 C2 plus 3 sigma v. Okay, so if I pass the plane through here, okay, these two chlorides will be reflected, right? So what does that mean? You will be getting the same structure. Similarly, along this chloride, okay, and along this chloride also, okay. And if I talk about the C2 axis, if you apply the C2 axis through the phosphorus atom and rotate it 180 degree, okay, so these, the places of this chloride will be changed, but the structure will not change. Okay, you will be getting the same structure. Or in case of C3, if you rotate the molecule 120 degree, okay, you will be getting the same structure, because in the hybridization is, I think, sp2, okay, that is having a bond angle of near about this 120 degree, trigonal plane. Okay, so you will be getting the same structure. And H is the horizontal plane, okay, because this molecule is planar, right? So you can see this horizontal plane, you just intersect all the chloride ions and the phosphorus, okay, so that will be your horizontal plane. So overall I can say this particular complex has a symmetry of D3H, right? So the last question for this assignment, you have to identify what is the ideal spectroscopic tool to observe Barry's pseudo rotation in this complex. Okay, and you already know that the Barry pseudo rotation is observed in the trigonal bipyramidal structures. Okay, okay, these are axial bonds, these are equatorials. Okay, so what can be the ideal spectroscopic tool? Okay, so IR tells about the bond stretching frequency. Okay, UV tells about the absorption at a particular wavelength, right? So the proton NMR tells about the changes in environment of proton. So basically proton is not there, so you can exclude this option. Okay, and what about the 13 NMR? It is basically tells about the environment changes in the carbon. Okay, so just try to give the answer. Okay, it is D, right? When the Berry pseudo rotation will take place, these two bonds will be interchanged, and this one also. Axial will be changing to the equatorial positions. I have already shown the typical example. Okay, this one. Okay, you can see this orange fluorine has gone to there, this place, and this green one has been interchanged with the blue one, right? So in this phenomena, what is basically changing? The environment of this carbon atom is changing, right? The electron density. Okay, so the bond length is different for this bond and this bond. So whenever this carbonyl will be going to this one, okay, the environment of this carbon will change. So that the chemical shifting in the carbon nucleus you can just observe by the carbon 13 NMR. So that will be the right answer for this. Okay. So thank you for attending today's sessions. It was all about from my side. Okay. If you are having more number of queries, you can just post them in discussion forum, and I will try to give the answers. Okay, thank you, Dr. Vidyalakshmi. So I am just leaving the meeting now. Thank you very much. Thank you everyone for attending this session.